Swayam Prabha. Digital India. Educated India.
Hello all. Welcome again to our NPTEL on Nonlinear and Adaptive Control. I am Srikant Sukumar from Systems and Control IIT Bombay. So, as always, we want to be motivated by this very exciting background image that we have. We want to eventually be able to figure out how to design algorithms that drive systems for autonomous motion such as this. So without delaying any further, we continue with our lectures. All right. So the last time we looked at a couple of myths and temptations which sort of plague typical asymptotic analysis, right? And after that, we moved on to some vector and matrix norms, basically giving us the ability to sort of deal with objects that evolve on normed linear spaces, right? So we defined norms on vector spaces and therefore gave them a structure which is that of a normed linear space. Right? We also defined what such norms are. We looked at a few examples of these norms. Right? So after that, we also spoke about the matrix induced norm, basically a norm that can be obtained by using a vector norm in order to construct a matrix norm, right? And this is called the matrix induced norm, right? So finally, we of course saw what is this normed linear space structure, and what is rather comforting for us is to sort of see that whatever spaces that we are usually going to be dealing with in this course are in fact going to be normed linear spaces, right? So now we continue and with our lecture. So we are on lecture number 3, right? And what we want to do is we want to look at a little bit more detail into the norms that we have constructed until now. Yeah, so it is very important that we get a better feel for the norms that we have designed. One of the key things in this direction is to actually prove that the norms we have defined are indeed norms, valid norms as per the definition. All right. So if you see, the definition contained 4 aspects. One is the non-negativity. Okay. Then we had the notion of the norm being 0 only when the vector itself is 0. Then we had the scalar multiplication property, and then finally the very key and very important triangle inequality property. All right. So we want to prove this, the fact that this infinity norm and also a particular p norm are valid norms, just to see how such proofs would go, right? So let's see. First we have this infinity norm, all right, which is essentially the largest component of any vector that is given to us, right? So if I have any vector in Rn, right, so if I say in this case we are assuming that x is in Rn, right? We are assuming that x is in Rn, and we are computing the infinity norm by taking the largest component of this, or largest element of this vector x, right? So since it's a finite dimensional vector, this is very easy, right? Remember we talked about the notion of supremums and maximums also last time. So if the set is finite, computing a maximum is very easy. Yeah, just have to compare, right? We also saw a couple of examples in this direction, in fact. All right, so let's look at the proof. So the first is the fact that the infinity norm is greater than equal to 0 is very obvious. Why? Because we are comparing absolute values of the components. All right, we take every component, we compute its absolute value, and notice that this quantity is always positive, right? So since this quantity is always positive, the maximum of this quantity also has to be positive, right? Well, non-negative, right? So if there is this element 0, right, then obviously the absolute value is also 0, right? However, this is always non-negative, right? So that's rather critical. And since we are taking a maximum over non-negative numbers, the output is also non-negative. So the first requirement is very easily satisfied. The second requirement is that it has to be 0 if and only if the vector itself is 0, right? And that's what I have written here. I have just written the statement, but it should be obvious that if I sort of try to expand a little bit, right? So this, if I have this guy, right, if I know that the infinity norm is 0, then what am I saying? I'm saying that max of every element is 0, right? All right, if the max of every element is 0, remember the absolute value is in fact non-negative, right? So if the maximum of all absolute value of xi is 0, then the only way this is possible is that xi is 0, right? On the other hand, if I start from here and I'm given that xi itself is 0, then it is obvious that absolute value of xi is 0, and this means that max of absolute xi is 0, right? And that's it. This is the infinity norm, right? So we have very easily proven that the infinity norm being 0 is equivalent to each component being 0, that is the vector itself being 0. All right. The third property, that is the scalar multiplication property, is rather obvious. It's nothing to do, because again you have an absolute value, right? So the alpha will come out here, right? And the alpha can be pulled here, right? So the scalar multiplication property is very, very straightforward. So I'm not really elaborating on it, right? Now we come to the rather critical triangle inequality property, and as always, whichever is the critical property is what is difficult to prove. Yeah, right. So always more challenging. Yeah. So let's look at this. Yeah, let's try to do this. So in order to prove that you have a triangle inequality property, I need to show that norm of x plus y, the infinity norm of x plus y, is less than equal to infinity norm of x plus infinity norm of y. Okay, so that's the first step, that's the last step. All right, now I'm just writing the definition here. The infinity norm of x plus y is simply max over 1 to n absolute value of xi plus yi. Okay, now it should be obvious to you that since I'm computing the max of xi plus yi, for some k this is the max, right? So for some k, this is in fact not less than equal to, but you can even say this is exactly equal to, right? I can even say this is exactly equal to. So what I can do is I can simply erase this, right? The infinity norm, that is the max of xi plus yi, is in fact exactly equal to absolute value of xk plus yk for some k, right? Because after all, I'm taking a max, right? So it has to be true for some I equal to k. Okay, and that's what this is, right? Now, by the triangle inequality property of the absolute value, right? So the absolute value actually satisfies the triangle inequality. This is very well known, I'm not going to prove it. Easily verifiable also, right? So from this triangle inequality on the absolute value property, I get that absolute value of xk plus yk is less than equal to absolute value of xk plus absolute value of yk. Again, for some k in 1 to n. Okay, for some k in 1 to n. Right? All this while this quantity is in the left, by the way. So I started with an equality, again an inequality, now I have an inequality, but all the while this quantity remains on the left hand side. Okay, so this is how we do a lot of inequality proving. All right, so get used to it. This is how we do a lot of inequality. We start with a quantity and keeping this on the left hand side, we keep doing inequalities and inequalities and so on and so forth. Yeah, usually one directional. Yeah, if we are doing less than equal to, it will always be less than equal to. If it is greater than equal to, it will always be greater than equal to on every step. Yeah, or equal to. It will never switch between less than and greater than, because then you cannot actually prove anything. Okay, so this is a very standard method of proving things. Right. So this is xk plus yk for some k in 1 to n, and this should be obvious that this is less than equal to max from 1 to n xi absolute value and max from 1 to n yi in absolute value, right? Because if I take any xk arbitrary for some arbitrary k in 1 to n and I take its absolute value, it has to be smaller than if I take the max over all possible such case, which is what this is, right? And it's now evident that this quantity is x infinity, right? And this quantity is y infinity. All right, so we started with this, we did a lot of inequalities, and we have proven that x plus y infinity is in fact less than x infinity plus y infinity. All right, so that's sort of the end of the proof. Okay, so we've proven that the infinity norm as defined satisfies all the norm properties and therefore is a valid norm. Yeah, all right, great. Okay, so now we want to do something very similar. All right, we want to do something very, very similar for our 2 norm. All right, so let's see if we can in fact do something like this. Yeah, so how is the 2 norm defined? So we are not, of course, dealing, I mean, similar proofs can be done for all p norms, but we are focusing on this infinity norm and 2 norm because these are rather important norms. So the 2 norm is the, like I mentioned last time, is a Euclidean distance, the way we know it, the way we know how to measure distance, right? And the infinity norm is, of course, rather important norm. Yeah, so we I mean, of course, you can do the same exercise for all other norms. Yeah, so I'm not going to do it for all possible norms, right? So it's defined as summation over 1 to n absolute value of xi squared, and then I take a square root. Okay, so immediately, very, very, in passing, I say that the first 3 properties are obviously satisfied. So I mean, I will still write a little bit here now. Okay, I'm still going to write a little bit. So if you look at non-negativity, that is, so this should be sort of evident to you, right? Because again, if you look at, you're taking square of absolute values, so it's a positive quantity, then I'm taking summation of this positive quantity, then I'm taking a square root of that, again a positive quantity. All right, so great, so this is fine. Yeah, this is good, right? Then the next one is that the 2 norm of x is 0 if and only if x itself is the 0 vector. Yeah. This is again something that is not too difficult to verify, right? So if I sort of try to compute, if I sort of try to write what is the square of a 2 norm, then I will get something like x1 square plus x2 square plus xn square. And suppose I say that this is 0, right? then the only way this is possible is that each component is 0. Yeah, it's very easy to argue this, right? Because if any of them is non-zero, then the outcome is non-zero. Why? Simply because we are only adding things. We are never subtracting anything here. Yeah, nothing gets subtracted here. Only things get added here. Right? So if anything is non-zero, it's definitely going to add something, and this will be not 0. So the only way that norm x2 square is 0 is if xi itself is 0, which means that the vector x is 0. Right? And similarly, if x is 0, if the vector x is 0, the fact that that is going from this way to this, that is, given my vector being 0 vector, then the norm is 0 is very, very obvious. Right? So the first two properties are this. Then you have the scalar multiplication property, yeah, which is that the 2 norm of alpha x has to come out like this. Any scalar multiplication has to come out like this. Now it should be obvious that this guy will expand to square root of summation alpha square xi squared, right? And this is simply that, and so that's it. We have proved this property, right? Very straightforward. Okay, which is why I said that they're obviously satisfied. But here you go. Just to be clear, we have in fact proved it. Yeah. Right. So now the triangle inequality, as always, our key or difficult property, if you may. Yeah. So we want to talk about the triangle inequality property. Right. So if you look at the square of the 2 norm for x plus y, again I have taken the quantity that I want on the left right here. It's going to stay like this. Then this can be expanded, or this can be actually written as summation over from 1 to n, I equal to 1 to n, xi plus yi squared. Alright. Okay. Now this quantity actually evaluates to this, the quantity inside the summation. The quantity inside the summation evaluates to this. Right. So let me sort of verify if this is the case. Alright, yeah. So the quantity inside the summation will actually evaluate to this. Yeah. And now what do I know? I know that this quantity right here is less than this guy. Yeah, not difficult to verify, right? Because the 2xi yi is only going to reduce xi squared plus yi squared. Yeah, and square makes the signs positive, right? So the 2xi yi is always going to bring down xi square plus yi square. It's you cannot guarantee that 2xi yi is sign definite. That is, 2xi yi cannot be guaranteed to be positive, right? Therefore it can be positive, which would be great, right? Yeah, let's see if this is correct. Let's sort of think about this a little bit more carefully. I think I said that in sort of passing. So if I evaluate this is xi squared plus yi squared plus twice xi yi. Yeah. So I think I should try to populate some of the intermediate steps, which would be better. So this guy is can I say that this guy is I don't think this would be quite okay. Yeah, in fact, how I would say it, yeah, so this is I would like to sort of rearrange how I say things here. So this is not, sort of completely right, I feel. So what you want to say here is that this is actually less than equal to xi square plus yi square plus twice xi yi. This is what makes sense. Yeah, so this is not completely right. So there is an additional term here. All right, I hope that is sort of obvious to you. Yeah, I hope that is obvious to you. Now the rest of the steps I have to sort of rethink. This logic will not work anymore. So this is now I would like to work on this term. Yeah, I would like to work on this term, and what I would want to claim is that this guy, yeah, is less than or equal to twice norm x and norm y. Okay, I would like to claim that this is what is happening. All right, this is what I would like to claim. Okay, does that make sense? Because if that happens, if this is true, okay, so if so let's see, if true, then this right hand side entire thing becomes actually equal to or less than equal to so if you see, this quantity is the 2 norm of x squared, and this quantity is 2 norm of y squared. So this is actually something like 2 norm of x squared plus the 2 norm of y squared plus twice the 2 norm of x and the 2 norm of y. All right, so now, and this is basically equal to norm of x2 plus norm of y2 whole square, and my proof is done. Because if you see, on the left hand side I had 2 norm of x plus y squared, and here I have 2 norm of x plus 2 norm of y whole squared. So if I remove the squares on both sides, my proof is done, right? Okay, all right. So now what am I left to prove? I am left to prove this guy. Okay, all right, let's see if we can. We'll try to do it. If I cannot, I will probably show it to you next time. All right, but let's give it a shot right now. So I have twice summation over I xi and yi on the left hand side. All right, so which is and the right hand side, so this is the LHS, the RHS is twice summation over I xi squared multiplied by summation over I yi squared. And I think I'm missing a square root here. So I'm missing a square root. All right. So does this look very easy, obvious? This is something that I will have to probably get back to you on. I'll have to think how we will do this proof there is some smart use of Cauchy-Schwarz that I can directly do, yeah, but I don't want to do that. Yeah, I want to do it on this particular case, yeah, rather than try to employ a general formula. Okay, let's see. Yeah, so you can see that this even in this simple proof we sort of get into an interesting sort of turn, right? It's not that it simply goes through like we would want. Yeah, the terms look rather similar. Yeah, the 2xi yi and 2xy look very similar, but actually they are very, very different looking terms. Yeah, when you expand them, so the LHS actually looks something very simple like this. The right hand side is this, so it's like you have square root and so on. So I mean, how I would think of approaching this is that I will take a square of this, right, and then I will have terms like sum xi square and summation of yi squared, right, and then I would like to see what happens, what happens to each of these, right? So I want to see that how to deal with each of these terms, right? So because then I'll also have to take a square here, in fact a square outside, right? And if I take a square outside here, then I'm left with a square of sum of products, right? And then I have to sort of correlate these. Okay, then I'll have to correlate these. Yeah, so and my aim is to sort of just prove that one is smaller than the other. So let me actually think this piece of proof I will actually cover again next time. Yeah, let's not worry about it. But the point is you will eventually see that the 2 norm also is a valid norm. Yeah, you will actually complete this proof. We have already verified the first 3 properties, which were rather easy. The triangle inequality property of course is a little bit more complicated to prove. So we will look at this proof. So after that we want to look at notions of convergence. Okay, so that's what we want to do next time. Yeah, so that's the plan for next time. So once we understand the notions of norms, how norms work, we want to talk about convergence. That is because in order to actually define convergence, you need the notion of a norm. Yeah, because otherwise you cannot actually convergence means basically going close to something, right? So like we discussed, the entire idea of going close to a point cannot be easily defined in vector sense if you don't have a norm. Yeah, and so once we have a norm and a norm linear space, it's easy to prove convergence. All right, so that's what we are going to do next time, right? So so what did we see today? All right, so what we did today is rather basic proofs of which norms are actually satisfying these norm properties, right? So we are yet to prove the norm property for one of them, right? But we looked at how to prove that the infinity norm is actually norm. We are still to see the triangle inequality property for the 2 norm, and of course this is all leading up to actually defining convergence, Cauchy sequence, and inner product spaces and so on and so forth. Yeah, so convergence is a rather key key property for us, which is what we will look at next time. All right, thank you.